since this will be the last couple of hours of your lessons, we would like to thank you for these wonderful lessons.
Thank you very much.
On behalf of all the organizers, thank you.
Thank you very much, Elena.
You can start, please.
Okay. So, hello, everybody. So, in today's lecture, I will continue with the report and the introduction of the Axion experiments. Now, but as usual, we should start with a recap from the last time. In the last lectures, I was telling you how Axion dark matter is supposed to be produced in the early universe, and how the Axion dark matter abundance depends on the essentially only just on one parameter, or sometimes on two. So in the case of the pre-inflationary scenario, it depends on the mass, or you can translate this, of course, into the decay constant, on the initial angle with which it starts, or which has been taken in the observable part of the universe. While in the post-inflationary Pichet-Quinn symmetry breaking scenario, it depends only on the decay constant, or equivalently on the mass. So, and as we have seen, in the Axion can be 100% of dark matter in the pre-inflationary scenario produced by the so-called solely by the misalignment mechanism. It can have an arbitrary small mass or arbitrarily large decay constant, maybe not for the not usual Axion, just up to the decay constant up to the Planck scale, but for the Zn Axion, it was even possible to have essentially a smaller mass, not a larger Fa, but a smaller mass corresponding to the same decay constant. But so you can populate. So for the pre-inflationary scenario, the Axion can be as light as 10 to the minus 10 electron volt, and then up to masses of the order of say 10 to the minus 4 electron volt, or an Fa of 10 to the 11 GeV. You do not need any fine tuning. So to say, the least fine tuning you get in this mass range, say between micro electron volt and hundreds of micro electron volt. At the upper end, you have to tune the initial angle, so the initial value of the Axion field in units of the decay constant to about pi, and for in the other region below the micro electron volt, you have to tune it. But it was, the tuning was not so bad. For example, even for a gut scale Axion, you need a tuning to 10 to the minus 3 or something like that. It's not comparable to the tuning which you have to do for the theta parameter in QCD, that it should be less than 10 to the minus 10. So, but there was also this other mechanism, this post-inflationary mechanism, in which because you had to average over the initial values of the angle, because in the observable universe, the observable universe is consisting of many patches which had different initial values. You have to average over that, and therefore, in this case, you would get an overclosure for too small Axion mass. There is a strict lower limit on the Axion mass in this case, which is 28 plus minus 2 microelectron volt. So otherwise, so if it's smaller, then you have an overclosure, you have too much dark matter. Then there's a region, unfortunately, even in a domain wall number 1 case, or in general in this post-inflationary scenario, there is also a contribution for axion dark matter arising from the decay of the networks of topological defects and like cosmic strings. And so it's hard to really simulate them with the physical parameters. So you have to, because the universe is so large, it uses of this cosmic string radius and so on. So therefore, there is still a considerable uncertainty. So the mass may really range from say 57 microelectron volt up to 100, even up to a milli electron volt, maybe less, maybe hundreds of microelectron volt. So this is unfortunately quite an uncertainty, because in principle it should be possible to narrow this down if you can really make reliable predictions from the contribution of topological defects. There is of course, depending on the ultraviolet completion of the Axion model, you can have domain wall number 1, or you can also have domain wall number larger than 1. This depends essentially on the anomaly, the color anomaly. And for the simplest case, for example, for the KSVZ axion, we had seen that the Patrick-Winn symmetries or that the axion decay constant was identical to the Patrick-Winn symmetry breaking scale, but in other cases it can be just a fraction of the Patrick-Winn symmetry breaking, and so this fraction is, or the fractional factor is a natural number, and it can be larger than 1. But in this case, you have long-lived domain walls. In the case of domain wall number 1, it is only short-lived, but in the case of domain wall number large, the domain walls are long-lived, and they also give quite a substantial contribution to the axion dark matter, and therefore the lower limit on the axion mass is even higher. So it's about 100 microelectron volt, and so in this case, the dominant or the expected axion mass, if axion makes 100% of dark matter, is even larger. And there are other mechanisms which also, like this kinetic misalignment mechanism, which would also be at work for the Zn axion, which I mentioned in my second, or what was it, the third, in the third lecture. This also favors the higher axion masses. So, but at the moment we don't know whether there is a pre-inflationary Patrick-Winn symmetry breaking scenario, or it's post-inflationary. We don't know the domain wall number. We don't know the possibility maybe that you have this so-called kinetic misalignment. So we have to consider that the axion, the dark matter axion mass spans really a huge range, and these are many orders of magnitude in mass, and therefore also in coupling. So the coupling is inversely proportional, so they can be very lightly coupled and stronger. Okay, so then in the last lecture I was talking about axion dark matter detection experiments. I started, and I gave also their the current limits made by such experiments like ADMX and this RBF, Rochester, Brookhaven, Fermilab, University of Florida, and so on. And so we have seen that with the technique of microwave cavities, so microwave cavities in strong magnetic fields, a resonance search for Axion to photon conversion in the strong magnetic field, one could cover, so to say, so what or one is supposed to cover with the next generation of microwave cavity experiments, something between a few times 10 to the -7 electron volt up to about 100 micro electron volts. So this is about the range. So organ is the one which has the highest, which at the moment has the highest, so to say, resonance frequency. And then I have, and then I have also talked about experimental proposals to go to higher masses. These were the so-called dish antennas. So and dish antennas, which I was mentioning, was this MadMax experiment using really several dielectric discs and so on. And there was this brass experiment, which wanted to use really big mirrors, big magnetized mirrors, and collect then the generated light by these mirrors. So this is another kind of dish antenna. Then there is this bread and there's the lamp post, which are acting at different regions. But so this is, and I also mentioned this 2-rod, which uses, instead of a real magnetized mirror, some topological insulator. So these are these kind of proposals which are acting in this higher mass range. And now we come, so this is now what I'm starting with today, is to look for or to introduce you to the experiments which are searching at lower masses below the microwave cavities. So these are experiments in this region below micro electron volt or something like that. And so these are searches employing lumped elements. So we will start now with one of these proposed or a whole suite of different experiments. So the idea is to search for an Axion-induced magnetic field. So again, the interaction which is used is this E dot B interaction, which so the two photon or this this E dot B interaction. Now, so these searches for Axion-induced magnetic fields were proposed by Pierre Sikivi, Sullivan, and Dave Tanner, and later also by Kahn, Safdie, and Thaler. And so they start. So there are two different geometries which one will want to use, but one is looking for a similar effect. So I start now with a description of it. So you suppose you have a toroidal magnet with a fixed magnetic field. So this magnetic field should now go around this toroid. You have this kind of toroid magnet, and then in the presence of Axion dark matter will generate an oscillating effective current, as I said, because the Axion field itself is oscillating with the frequency of its mass, of its rest mass. So it has this so to say, it's oscillating like a cosine of the mass times the temperature, the time, and so because of this E dot B interaction, it generates an oscillate effective current parallel to this magnetic field B. So there is an effective current, and this effective current is proportional to the axion, to this axion coupling to the two photons, or to this E dot B, times square root of 2 times the density of dark matter. This is essentially proportional to the amplitude of the axion field. So this is the amplitude of axion field quotient MAT times this times this field B. So it goes along this B0, and this current, the effective current, is proportional to B. Similarly, if you have a solenoid magnet with a fixed magnetic B0, then the axion dark matter again generates an oscillate effective current parallel to B0. In this case, it's along the axis of this solenoid. So here I have this effective oscillating current, and here you have in this direction the effective oscillating current. Now this oscillating current, now look again in the toroidal case, generates an oscillating magnetic flux B through the center. So it will be through the center, or in the case of the solenoid, it produces a flux which is azimuthal, so to say. It's going here around, and it's oscillating. Now, and this this flux, this B flux, this oscillating B flux, or this oscillating magnetic flux can be read out by a pickup structure. So you suppose you have here a pickup loop, or here pickup loop, and then you can measure this this magnetic flux, or you can detect this magnetic flux. Now, there have been already pathfinder experiments now using this kind of technique, and so the first one which was already also publishing data was Abracadabra, really long name, and I don't remember now exactly what the acronym means, but a broadband, yeah, I don't remember. So, but so here you see how it looks like. So this first experiment was really small. So these are all kind of tabletop experiments. And you can here see the sensitivity of this experiment. It was it had this kind of toroidal configuration, and they were searching, so to say, here in this megahertz range, and could reach a sensitivity in this axion photon coupling, which is barely touching cast. So of course it's far away from the axion at the moment, but this Abra was just a magnet with a diameter of a toroid with 10 centimeter diameter. So it was really a small thing, just to make it demonstrate a proof of principle of this method. And there was also 1 year later ADMX SLIC. So this looks like that. So they have this kind of solenoidal magnet configuration, and they were just they did not really scan some parameter range, but they measured at three different configurations. And then there was this experiment Shaft, which uses again the toroidal configuration, they published in 21 and scanned already quite a big range. The advantage of this is that you can work with it in a broadband mode, so to say. And also in Hamburg, we have this proposal. So this is not, this 21 is not the publishing of the first data, but the publishing, so to say, of the idea or of the letter of intent, but it's not really letter of intent. So everything what is needed for this experiment is already in place. This is the so-called WISP-LC experiment, run by Dieter Horns and his group in Hamburg at the university. And what is the difference to these other experiments is that they have really a huge, they have a magnet with 14 Tesla. So it's really, and which has also quite a much bigger volume than the other experiments. Therefore, this experiment is supposed to have a much higher sensitivity, so compared to Shaft and Abracadabra. So this is the predicted sensitivity if they are working in this broadband mode. And here is the sensitivity if they just look for the resonant mode, which normally takes, of course, out a longer time. And here's the comparison with ADMX SLIC. Now, still, as you will see, so most of these experiments are still quite far away from the Axion. Also, I mean, here what you see, this gray line, this is the prediction of the ZN Axion model where it produces the 100% of the dark matter and is at the same time solving the strong CP problem. So in this region, so they could even probe this region with a little bit with the resonant case for WISP-LC. So that's nice. Now, but so there are ideas, or there has a consortium has been forming in US as part of a DOE Department of Energy new initiatives in dark matter program. They have now set up this dark matter radio cubic meter consortium. So they want to go from this small volume really to big volumes. And there are so people from Abracadabra and from Shaft and so on. They are working together, and the aim of this consortium is of this dark matter radio cubic meter consortium is really to reach the canonical Axion band. So with this dark matter radio cubic meter, and then maybe later with a dark matter radio gut, really to probe it also to smaller masses of nano-electron volt, which should remind you now on the predictions from grand unified theories. So this dark matter radio cubic meter consortium aims really to reach the canonical Axion mass, even reaching the predictions from grand unified theories. So this will of course still take a lot of time, and not everything is funded, but so they are starting. And of course, I mean, so here these were the first lumped element experiments. Now they want really to go really deep here into the parameter space. So we have seen now so that these planned helioscopes may indeed cover the whole mass range within the foreseeable future. So we have discussed these lumped element searches like dark matter radio, WISP-LC, ADMX SLIC, and so on. But so this dark matter radio is what's really to go down here, and in the extremely busy is the micro electron volt range. That's clear because here that the techniques is there, and also, I mean, the so to say the case. The case that something is in this region is also very nice, because in the pre-inflationary scenario we don't have to fine-tune at all, and in the post-inflationary scenario, of course, there's this lower limit. You have to go really to the highest masses. Here it gets a bit tricky with the microwave cavities. So therefore we have seen, so there was really also was really very well motivated to think on new methods like these dish antennas, where one also can probe this kind of range. Now, if you see, so I mean, these are maybe sometimes optimistic, but maybe also, I hope so, also realistic expectations. So you only see a few windows of opportunity for newcomers. So here, for example, I emphasize, so in this range there is still a hole, and in this range there is still a hole. So if somebody wants to do something and be alone, so to say, then has to concentrate on these regions. But I find it really amazing. So I mean, when I started to work on this Axion physics in 2006 or something, or 2003, there was no idea that one could. So nobody would have ever thought that one would be able, so to say, to dream to reach such a sensitivity over these huge mass ranges. So, and of course, at this early in 2003 or so, I mean, it was still probably the people were mainly thinking were mainly thinking that dark matter is in WIMPs. So and nowadays the big WIMP detectors, the direct detection detectors, they come nearer and nearer in a quite wide range to the neutrino floor, and also at LHC there was no hint of any WIMP candidate until now. So this probably made this community think about alternative dark matter candidates, or more about alternative candidates. And now, so there are this quite a number of experiments starting to do this. So, but I should also emphasize, so if some of these experiments sees a signal, the nice thing about the signals, of course, they are very, so the signal is, so to say, a very thin line, and it determines so you can determine from that very accurately this Pechet-Win or the Axion decay constant, and you get from that a hint on the Pechet-Win symmetry breaking scale and these things. But this you can only do if you make the assumption that this was really that this particle was really an axion, because otherwise the connection between the axion and the decay constant is not there. So this arises via QCD. So so it would be so in a sense. So if some of or one of these experiments detects this candidate, so of course surely they will get a Nobel Prize for the discovery or the detection of the dark matter, for the direct detection of dark matter. But on the other hand, they will not get the Nobel Prize for the axion, because if you want to prove that it's an axion and not just an axion-like particle, you have to determine its coupling to the electric dipole moment of the nucleon, because the axion was introduced as a space-time dependent theta parameter, And the only and this is the guaranteed coupling, so to say, of the axion, and only the axion can make this. So one should in addition see that this dark matter candidate has exactly this coupling. And there was a genius idea by Graham and Rajendra, a genius idea I found, that one could also do axion dark matter detection via magnetic resonance searches and using the EDM coupling, the nucleon electric dipole moment coupling of the axion. So how is this going? So now, so of course, I mean, so we are sure the axion has to couple linearly to the nuclear electric dipole moment. And if we have now an oscillating axion field, this means all the nuclear electric dipole moments, should oscillate, so to say, with the frequency of the axion. So you get the axion dark matter field will induce an oscillating nucleon electric dipole moment. Again, the oscillation goes with the frequency of the axion mass. The amplitude is proportional to the square root of the dark matter, and of course the whole effect is proportional to this nucleon electric dipole moment coupling. Some people call it always GD. I call it GAN gamma, but I use this notation now in these plots because I want to use the plots of these experimentalists later. So, okay. So as I said, the axion dark matter field should induce oscillating nucleon electric dipole moments, according to this formula. Now, so the idea of this gentleman were one should place a ferroelectric crystal. Ferroelectric crystal means that in this crystal you have permanent electric polarization fields E star. So and they are, so to say, they are inside this crystal, so to say. So take place such a ferroelectric crystal in an external magnetic field, which should be perpendicular to this permanent electric polarization field of this ferroelectric crystal. So you have this kind of configuration. Now, then in this case, then the nuclear spins in this ferroelectric crystal, they should be polarized along. They are then polarized along this external field, magnetic field, and precess at a Marmor frequency 2 times the nuclear magneton times this external the magnitude of this external magnetic field. Then, but there is an interaction, which is induced, which or there's an inaction of the dark matter induced nucleon EDM with the E field. And this is this interaction. So this is proportional. This is so to say the EDM times this internal electric field. This interaction will lead to the resonant increase of the transverse magnetization of the sample when the Larmor frequency hits or is equal to the mass of the axion. So you get to this interaction, you get such a resonant increase of the transverse magnetization. And of course, the transverse magnetization you can measure with, or you have access to via magnetic resonance searches. So there is an experiment of this type is currently being set up in Boston, which is called Casper Electric. And this Casper Electric is being built in different phases. In the first phase, it will still be far away from the prediction of the Axion EDM coupling. But in phase 2, it starts really to dig into the Axion motivated parameter space, and in phase 3 it really can cover a whole lot of this mass range. So in phase 3 it will probe Axion dark matter in the mass range predicted by grand unified theories, and so this is really spectacular. But of course, you could say now, but if the Axion mass is 10 to the -6, so in the range of ADMX, it's really sad that one cannot go there. I mean, the problem is, so to say, that you can only go that you can increase the sensitivity either by going to higher magnetic fields, but this cutoff you can't avoid. You have to increase the magnetic field, because you should increase the Larmor frequency in order to go to higher masses. Now, if you have a fixed magnetic field, then you cannot do anything against the natural value of the value of the nature of the nuclear magneton. So the only thing what you can do is to increase the magnetic field. And at some point, but in fact, I'm sure if ADMX or so is finding a signal, then one has to go along this line, or use similar methods using storage rings. For example, with storage rings, you could also look for Axion dark matter by looking for resonance effects in them. Like so similar to G-2, but I think this has to be done at some point. So I'm sure, or more or less quite sure, that the Axion will maybe first seen in or the probability is high that the Axion will be first seen in the photon coupling, but at some point one has to think about how to measure its coupling to the nuclear electric dipole moments in order to be really sure that this is the Axion. Okay, I think I'm doing it now. No, this is I have a last slide here. I wanted to emphasize here for the so here is again the plot relevant for the similar plot where we have also the prediction of the ZN Axion dark matter model, and of also the prediction where the Axion is 100% of the dark matter. And there, if you compare this with that, you see also that you could probe this so to say with Casper phase 2. With 1 and 2, you can already cover the ZN Axion dark matter, but you even don't have to go to the Casper phase 3. So, okay. So are there questions up to now? Hello?
Any questions? Comment? I don't know. I think you can decide or either to continue or to have a small break of 5 minutes.
Then we do a short break,
Ok.
5 minutes. Okay.
Ok.
At a quarter to
Exactly, a quarter to.
we meet again.
Exactly.
Okay. Yeah.
Bye bye.
Bye.
You can continue.
Okay. So then I continue.
Very good.
Now, until now, I have, in terms of Axion experiments, I concentrated on Axion dark matter experiments, but there are other experiments which in which you can look for axions. So one of the class of experiments are the so-called light shining through a wall experiments, where you are really produce and detect the particle in the laboratory. So you don't have to use some other agent in the universe or astrophysics in order to produce the axion, but you produce yourself and you detect it. Of course, you have to pay the price of twice the coupling constant squared, so to say, then which makes it which makes it hard to reach really very good sensitivities. And there are these other experiments where I look for astrophysically produced axions, namely if you now concentrate on the experiments which you are doing on Earth, then searching for solar axions. So I start with the light shining through wall searches. Again, so what you are looking for is the coupling of the axion to E dot B. So now, due to this interaction, the axion experience a mixing with the photon in an external magnetic field. So with this, we have now several times exploited also in the dark matter experiments. So therefore, you may set up a light shining through a wall experiment to search for the axion. So the idea of a light shining through a wall experiment is, because of so you send a laser beam or a photon beam along a transverse magnetic field. And because of this two photon E dot B interaction, the photon can convert or oscillate into an axion. The axion can, of course, fly through a wall. And behind the wall, you again set up a magnetic field, a transverse magnetic field. And then the axion can reconvert, because of this two photon interaction, into a photon. And and in general, if the photon energies are much higher than the axion mass, then this, so to say, that the photons behind the wall will have exactly the same frequency as the photon before the wall. So there is so to say, you are looking just for photons which arrive behind the wall with the same energy, or with the same frequency. Now, the probability that a photon with omega with an energy much larger than the axion mass converts in an axion after having transferred a distance LB in a magnetic field is given by this expression. So it is similar to the case of neutrino oscillations. You have this system has, so to say, the photon axion system has a certain oscillation length, and the oscillation length is given by 4 omega, 4 times the energy of the photons, divided by the mass of the axion squared. In neutrino oscillation, you would have here a delta m squared, the mass squared between the neutrino flavors. Here is you have just an ma squared because the photon is massless. So this is what you have like that, and then so as you see that that you get the best sensitivity if this oscillation length is much larger than the magnetic field, so that you can get a convert, so to say, a continuous conversion, so to say, of the axion into photons over the whole length of the magnet. And in this case, so if ma squared lb is much larger than 4 omega, I said it the other way around, but this lb should be much larger than the oscillation length, of course. Then you get then this light shining through a wall probability just goes very simply like 1/4 the coupling Ga gamma times B times the length of the magnetic field squared. So you see, of course, so this, but this factor, of course, you have to pay twice. So this is now for if you do light shining through a wall, you have to take the probability that a photon goes into an axion, but the axion goes again to the photon. Then it will be proportional to 1/16 GABL to the fourth. So you get a suppression, of course, in the fourth power of this photon component, but you get, so to say, quite an enhancement times of B times L to the fourth power from the length and the strength of the magnetic field. So the figure of merit is of course B times L should be very large in order to get a high probability of conversion. Now at DESY, we were doing a first experiment, light shining through a wall experiment in 2000. I think we started in 2009 or so with the experiment, where we were using one of the Hera magnets, which was already on the test stand. We used this magnet for a light shining through a wall experiment. So the wall was in fact really inside the magnet. The magnet has a length of 8.8 meters. So this LB is then 4.4 meters. Then we had the wall, and behind the wall we were then behind the wall, or at the end of the thing we had a detector. So what we used, we used a laser. We were collaborating with the Albert Einstein Institute in Hanover, who were developing the advanced LIGO laser, and we used the same kind of primer as the same kind of advanced LIGO laser for the primer to get the primary power of laser photons, first the infrared. Then we were frequency doubling this because we had only a detector which was good in the visible range, just a CCD. And then we did this light shining through a wall experiment. We set up in the part before the wall. We were setting up already a cavity, a Fabry-Perot cavity, in order to have more power, to be able to laser power, in order which can then be converted into photons or into axions. And so the power inside this cavity was about 1 kilowatt. And then so at that time, so we were in a race, so to say, with Oscar at Cern. We did also light shining through a wall experiment, but they were using two LHC lasers in the test stands. but not such a powerful laser system. But they could, so after a short time, they were beating us. So you see, but it's still at the moment the best purely laboratory limit on low mass Iaxo-like particles is given by ALPS 1 and the Oscar data, and you see here one was reaching something like a few times 10 to the minus 8 GeV to the minus 1 in the photon coupling, up to a mass of the order of a milli-electron volt. At some places, ALPS is still better than Oscar, because we did some, but at the low mass, Oscar is a factor of few better. But of course, one should note that this sensitivity is still by many orders, by more than 2 orders of magnitude, excluded by the helium burning star bounds and by the helioscope bounds for solar axions. However, it's really, so it doesn't rely on any assumption about astrophysics, and therefore I think it's good to have also such a very solid limit. But of course, after we have produced this or reached this sensitivity, we were thinking how to really to increase the sensitivity by this more than 3 orders of magnitude, or about 3 orders of magnitude, in the coupling, how we can increase this sensitivity in order to really step into new land in parameter space, which was not already excluded by astrophysics. And so the idea was then, I mean, I have proposed this already in 2003, but now one could really think of really doing it. So before it was the idea of a theoretician, but now the experimenters really, they took it over, and then we set up ALPS 2, or we started to think about ALPS 2, and then in 2013 we had a technical design report, and ALPS 2 is now a collaboration not only with the Albert Einstein Institute in Hanover, but also the University of Cardiff, University of Florida, and University of Mainz are involved. And what was the idea? Of course, so we wanted to increase the sensitivity in the photon coupling by a factor of more than 1,000, because we should reach something like a few times 10 to the minus. So we want to reach 2 times 10 to the minus 11 in GeV to the minus 1. And so ALPS 2 is now at the moment being set up with 12 plus 12 straightened Hera magnets. One had to straighten the inner tubes, so to say, of these magnets, because they were, of course, these magnets were for the proton ring at Hera, and they were in the ring-like sections of Hera. So the beam tubes, they are curved, and one had to straighten them in order to, because light is of course only flying straight. So we had to straighten these magnets. They were straightened, and so we have now a length of 124 meter production cavity. And 124 meters regeneration cavity in one of the straight sections. So Hera has 4 straight sections. It's at Hera North, where there was before the H1 experiment. There is now the ALPS experiment. So the idea was to increase the sensitivity, of course, now by a huge factor. This gives a factor of 24, because before we were using half a magnet of Hera. Now we are using 12 full magnets on one side. So this gives a factor of 24 in sensitivity already. And then the next thing is to use optical cavities both at the production and the regeneration side. So in order to have a much larger power buildup, so that now the idea is to reach 100 of kilowatt instead of 1 kilowatt laser power. And on the other side, we also have a regeneration cavity, which increases then so to say the photon part of the Axion photon wave system behind the wall, and for the detector at the end, we are using two different detection techniques. One is heterodyne, and the one is a transition edge sensor. We are using now directly infrared light and do not any frequency doubling, because it's easier to use all this technology and also these high reflective mirrors and so on. They are all developed by the gravitational wave community, and therefore it's so we are profiting very much from that all these things for infrared has been very much developed by the gravitational wave community, and so we thought this is the best way, so to say, to proceed. Now the construction of ALPS 2 is progressing at DESY. All the 24 magnets are installed and aligned. Clean rooms at the end stations are operational. The commissioning of the optical system has begun. The alignment of the lasers with the beam tube is accomplished. You see here the beam spots, so to say, after having transferred all the 280 or nearly 300 meter through the beam tube. And a test operation of the magnets is ongoing over Christmas and over the New Year. All this was cooled down. Now it's at 4 Kelvin, the whole string, and the current is being set up. So recently we had 3000 ampere, and so all these tests are ongoing, and the first science run is scheduled for later in this year. So it looks like this picture is this whole ALPS string. It looks as if it were curved. Of course, it's a straight thing, but I like this photo because then it looks more like a laser interferometer, because we are using the gravitational wave experience and all these things. So at the end, even a straight light shine through a wall experiment looks like a gravitational wave interferometer. Okay, so ALPS 2 is designed to beat the astrophysical constraints and check the astrophysical hints of axions. So so here you see what kind of sensitivity increase we have projected. So this was here are the limits on the Axion photon coupling versus the Axion mass from ALPS 1 and from Oscar. And now with ALPS 2, we want to reach this. So this is our design sensitivity, 2 times 10 to the minus 11 GeV to the minus 1. And as I said, at low masses, it really touches this hint from anomalous energy loss of helium burning stars. So one really touches into that. Not the whole region is in reach for us, but quite a sizable region, and also a sizable region for the explanation of this anomalous transparency of the universe for TV gamma rays is also checked with ALPS 2. And as usual, so we understand that at higher masses, this coherence is lost, and then we have these oscillating features, so to say, in the limits. So in order to go out to proceed to higher masses, the easiest way would be to go to higher photon energies, but all this technology is not available. So there are no such good mirrors for visible photons, and so it's hard to go to the right. Here you see something which goes to the left. These are proposed next generation light shining through wall experiments. So there was an Italian proposal, Stax, where it was proposed to use as a photon source a gigahertz gyrotron. And so in principle, one can reach really, so if one has really a powerful gyrotron, one could have really a high number of photons, so to say. However, the challenges of the microwave range is really one cannot profit from such a resonant photon regeneration. One can have on the production side, one can of course increase the power, but on the regeneration side, there is no idea about that. And then also the single photon detectors in this range, they are hard they are not easy. Then was another proposal is to do ALPS-3, also known as URA, the joint undertaking for the research on axions. It's called URA because one would rely very much on Cern. So here is the idea to have 2 × 426 meter long string of the FCC HH magnets, which have a 13 Tesla and a megawatt scale optical resonator. And with that, you could really go down here. However, you see there's still some place to reach the nominal axion band. Also, of course, as I said, so I mean, there are meanwhile axion models which can live far away from this band. So in principle, one can also discover axions in this ranges. So it's not really so necessary to really dig into this range. So these are the light shining through the wall. So then I come to the helioscope searches. So for the the sun should be a very, very, very good producer of axions if they exist. So here I've showed the prediction of the flux of solar axions produced by the 2 photon process in the core. So this would be the production diagram, and you see the axion flux will be peaked because the sun, or in the core of the sun, there are temperatures of the order of keV. So there's no wonder that this flux of solar axions has a maximum in the keV range. So this one should have in mind. Here, the flux is shown as for photon coupling of 10⁻⁻⁻, GeV⁻⁻1. Of course, this flux scales with Ga gamma squared. So I mean, you square this diagram, so you get this. So this flux, it goes like this squared. So if you go to 10⁻11, then this goes down by 2 orders of magnitude. So the other one, so and there could of course also be a flux which I did not show now, but there could be even a higher flux if there is a non-negligible axion electron coupling. Then you get from axion Bremsstrahlung, you get an additional contribution which can be even higher. So this gives, so to say, the Axion photon coupling gives the minimal production, and in the KSVZ type Axion model, of course, the dominant coupling will be the Axion photon coupling and not the Axion electron coupling. But in a more general model, it could be more. So then, as I said, so therefore one expects really that the Sun is a good producer of axions. And then in the seminal paper of Pierre Sikivi in '83, where he proposed the helioscopes, he also proposed the helioscope search. Said one should point a dipole magnet towards the Sun and equip it with an X-ray detector, because now the solar axions, they can convert in this magnetic field into an X-ray photon, and the X-ray photon can then be detected with this kind of device. And it's, of course, it's exactly the same formula for light shining through a wall is also here. I mean, here's also light shining. Here's now Alps shining through a wall. So, or the sunlight shining through a wall. Yeah. So it was produced in the sun. Of course, this telescope should be shielded from the usual light, or also from X-rays and so on. But so the idea is very, very simple, but you have to set it up. And there were some prototype experiments also in Japan, and up to now, or until now, the most sensitive helioscope was the Cern Axion Solar Telescope, or in acronyms CAST. So the Cern Axion Solar Telescope was using superconducting LHC. It's not an original. It's LHC type dipole magnet, and had X-ray detectors at both ends. I think even at both ends. And then they had some construction that we could point it to the Sun when the Sun was rising and when the Sun was going down. And one could not follow it all the time, because I mean, the LHC magnet was not supposed to do that, to be movable and so on. But they made the minimal construction that they had at least some time during the day they could do measurements. They were using buffer gas inside the conversion volume to extend the sensitivity also to higher masses, in order to really to dig into this Axion band. And we will later see but we have already seen very often the limit which has been achieved, and the limit was at low masses was exactly more or less pari with the limit from helium burning stars energy loss. So there was really very sensitive, and yeah. But now there is already, so there is a successor in discussion. It has already even there's a conceptual design report written. This is the so-called International Axion Observatory, Iaxo, this proposal. So for this proposal, one wants to use a large, or to produce a large toroidal 8-coil magnet. So toroidal, similar to the Axion, to the Atlas magnet at Cern. So you want to build a large toroidal 8-coil magnet with a length of about 20 meters. So the magnetic conversion volumes would be these tubes here inside this magnet, and you would have the magnetic field, so to say, then similar to a dipole field inside of the tubes, of course. Then, so these 8 bores would have a 6 centimeter diameter each, now 60 centimeter diameter each, so they would be they would be quite good. And at the end of this, one wants to have 8 X-ray telescopes and 8 detection systems. So the X-ray telescope so wanted to, I don't know what happened here. So this X-ray telescope would look like that. So you have such kind of 4 nested hyperboloids, and then you are so to say focusing the X-rays into a focal surface in order to increase the signal, so to say, and also the signal to background. And and all this should be mounted on a rotating platform with services on it and so on. So this it's a huge instrument. The proposed site for this has now been proposed by the collaboration is DAISY. Of course, this looks like it will be without a dome around it, but this is just for the artist's view. Probably there should be a dome around it. Also, this looks nice for visitors, I guess. So, but so this at the moment, this is still this is not funded. However, there's another, the prototype for Iaxo, the so-called baby Iaxo, is already funded. So this is a smaller prototype version of Iaxo, where one wants to exploit 2 bores of the dimensions similar to the final Iaxo bores. So this is the instrument will have 2 bores, and therefore also 2 detection systems instead of 8. The detection lines these detection lines here with the X-ray optics and so on is supposed to be representative of the final ones. The idea of a baby Iaxo is to test and improve all the systems, and so Cern has agreed to do the magnet technical design, and this is ongoing already at Cern. The construction site of baby Iaxo is also already decided. It's DAISY, and it's funded by DAISY, Cern, and an ERC advanced grant of Igor Irastorza, who is the spokesperson of Iaxo, I know, of baby Iaxo. The preparations at DAISY, they have already started. So the mount of this is already in place. Baby Iaxo will be mounted on something which was produced for CTA, for the Cherenkov telescope array. So we could use a prototype for this mounts from which was standing in Adlershof in Berlin, and now it's brought to DAISY in Hamburg and assembled. And the data taking may start in 2024 and 25. It's very important, we think, that it should be at the times parallel when still ALPS is also still in place and working. So in case that one can cross-fertilize in case of some detection or so, one could really learn something if both things are in operation. So baby Iaxo and Iaxo will probe really the MEV Mass Axion. The baby Iaxo will dig already a bit into this parameter. This parameter range, but Iaxo will really dig deeply in the so to say vanilla Axion band, and will be essentially also important in a mass range where it is difficult to do Axion dark matter direct detection experiments, which is very so we had seen only lamppost or so could work in the same kind of mass range. And what I also find very nice is that both baby Iaxo and Iaxo can also probe the electron coupling. This is because, of course, so we can on the detection side we are only sensitive to the photon coupling, but on the production side in the sun, the axions can be produced by Bremsstrahlung and can also be produced by the Primakov effect, by the two photon effect. And so what is plotted here is the sensitivity of CAST already, so the published limits of CAST in this parameter range, or in this parameter setup, photon coupling versus the electron coupling. And here are the sensitivities of baby Iaxo, and eventually some further extension of Iaxo, and compared with the preferred parameter range preferred by the white dwarf, helium burning stars, and red giant hints, which I have been talking about at the end of the third lecture, I think. So this brings me to the next end. I have still a few slides, but maybe first you can ask some questions regarding this.
Oh, please, any questions? Any comments?
Everybody's tired. Huh?
Means that they have understood everything. So
it's good. So then I will. So let's meet again at half past.
Do you want 5 minutes of break?
Yeah, 5 minutes of break,
okay. And then we can say at 30.
At 30, yes.
Okay.
Yes. Okay, good.
Good.
See you at 30.
Bye.
Bye. So I'm back.
Okay, so you can start again. Good.
Yeah, okay. So what I wanted to tell you now is something what was something unexpected somehow, which is also, I think, now important in the connection with Axion experiments. So I want to talk about gravitational wave searches with ALPS and co. So like ALPS and helioscopes, and maybe even dark matter Axion experiments and so on. So let us start with light shining through walls. So again, I mean, this is just a repetition. So light shining through a wall experiments like ALPS, they search for the conversion of photons into light particles and vice versa in a strong magnetic field. Now, it has been pointed out already by Gertzenstein in 1962 that you can also have essentially light shining through a wall through the magnetic conversion of gravitons. So also there is a similar vertex, so to say, for photon graviton conversion, and this goes like now gravitons, like photons, they are both massless, so there is not this sine squared factor is not there at all, and you get so the probability that a photon is shining through a wall by the conversion into a graviton goes like 8 pi g squared, where g is the Newton's constant, times b times L to the fourth. So it goes like 1 over m Planck to the fourth times b L to the fourth. So this is, and this is really, so we have checked this. I have written a review with Xavi Redondo about light shining through walls many years ago. And there we checked that this is the dominant, in the standard model, that this is the dominant way how to get light shining through a wall. Of course, we will see that at the moment we do not have to worry about that as a background, so to say. But we can directly compare this formula with the light shining through a wall probability via axions. So we have this 1/4 Ga gamma squared times b times L to the fourth in the mass range where if the mass is very small. So in the massless limit. But this means, so we have these two formulas. So in principle, any limit on light shining through a wall from axions, we can translate into a limit on light shining through a wall through gravitons. And in fact, if we interpret now the established limit by Oscar and Alps 1 about light shining through a wall, we get, so to say, we can interpret this, we can recast, so to say, this limit or translate it into a lower bound on the Planck mass. So because I mean now, so instead of the suppression by 1 over the Planck mass to the fourth, we have the suppression in Ga gamma to the fourth. So what this means, so if we take this limit, so to say, in Ga gamma, this translates in the limit on the lower limit on the Planck mass of 7 times 10 to the 7 GeV. So of course this is not so spectacular. We are about 12 orders of or 11 orders of magnitudes away. So but nevertheless, so I mean this is a non-gravitational determination of the Planck mass. So not via stars or anything, so or via gravitational bodies, but from this light shining through a wall experiment, which I find amazing. And the Alps 2 prospects would say that we would with Alps 2 we would get a lower limit on the Planck mass of 10 to the 11 GeV. So I was asked by Emil Dudas, maybe we could make limits on large extra dimensions and so on. But I think it's maybe one should think about this. But so recently, some colleagues from Alps, they have pointed out that we can get even a better limit on gravitons or gravitational wave on gravitational waves from so now directly on gravitational waves coming from astrophysics, so not the self-produced gravitons, but now the gravitational waves, stochastic gravitational waves from outer space. And so they have pointed out that one can produce upper limit on stochastic gravitational wave background by recasting the light shining through wall experiments in helioscopes. So because it's really clear, so if one considers now only, so to say, only the detector side of the light shining through wall experiments, then of course this part will be sensitive to any stochastic gravitational wave background due to graviton-photon conversion. So now, because you can ignore the other part, but you have this kind of magnetic conversion regime and or region, and from the published limits on the flux of photons which you get here, so to say, from the darkness. You can put an upper limit on the amplitude of the stochastic gravitational wave background. And in fact, so what they developed are bounds on the Axion. They have translated the bounds on the Axion photon couplet obtained by Alps, Oscar, and Cast into bounds on the characteristic amplitude of the stochastic gravitational wave background. And this is shown here. Now Alps and Oscar, so in these red and bluish and green lines, these are limits in the frequency region around a few times 10 to the 14 hertz. This corresponds to optical frequencies of light, so to say, and this is because the detectors for Alps, Oscar, and so on, they were of course detectors which should see light from lasers, from visible lasers, and therefore these detectors were just sensitive in this region. So that one could of course get only a limit in this region, but this region reached an amplitude on a characteristic strain of a stochastic gravitational wave background of the order of a few times 10 to the minus 26, which is really remarkable. And from the Cast limits, of course, also the Cast telescope, the conversion inside the Cast telescope, the gravitational wave conversion inside the Cast telescope, and the non-observation of such of KeV photons from this telescope puts an upper limit on the strain now in the frequency region corresponding to X-rays, which is about 10 to the 18 GeV. The detector was only sensitive in this region, but here they reached even a few times 10 to the minus 28. So this is already quite remarkable. And so I should say, and the projected bounds from light shining through a ball experiments and helioscopes, they would even go down to nearly 10 to the minus 30. Now, as far as sources are concerned, so or plausible sources in this frequency range, they are not, so one does not have them. So maybe merging primordial black holes or such things, they could be seen by Alps too. And in this Iaxo frequency range, I have not seen any predicted sources of gravitational waves in this range. But however, one never knows, and if you never look into this frequency range, you will never know. And of course, it's also possible to equip the Iaxo instrument with other detectors sensitive in another frequency regions. Of course, this is not there to look for gravitational waves for axions from the sun. It should be KeV, but one may equip these experiments also with other detectors, and then be sensitive in other frequency regions, which are maybe easier also, where there are maybe also more motivated sources. Now, interestingly enough, currently there's a community forming which seriously considers the search for high frequency gravitational waves. So this is quite some number of people. So they have written a white paper on challenges and opportunities of gravitational wave searches at megahertz to gigahertz frequencies. That is, at frequencies which are not accessible by the conventional laser interferometers. And and they have also, so to say, they have what means opportunities. So they have shown that there's a number of sources which are well motivated and which at the moment which could give rise to gravitational waves in the megahertz or gigahertz range, and so there is well motivation now to start a campaign to do also experiments there and not just keep all attention just to frequencies below 10 kilohertz. Of course, this range is very much this lower frequency range is very much motivated by astrophysics. However, every source above 10 kilohertz should be a BSM, beyond the standard model source, or will be an exotic source and would have nothing to do with what we know, so to say. And so this is really a very nice region to look for. And very recently, then it has been really seen that the techniques developed for axion detection may really be suited for gravitation detection at high frequencies. What is shown here is the characteristic strain against the frequencies and the current limits on the characteristic strain of stochastic gravitational waves. So this we were talking about this so established limits. This established limit from KAST. This is from Alps and Oscar, and here are some limits from ferromagnetic helioscopes, and their limit from a Fermilab holometer, and here from bulk acoustic wave devices. So there are some limits. However, as you see, so very recently there has been a lot of considerations that one may really dig or use the devices for axion detection in order to look for gravitational waves. So, for example, here's the proposal to use the Iaxo bore with a detector sensitive in the gigahertz range, in order to try to go in the direction to measuring, so to say, the gravitational waves from the beginning of the thermal plasma in the very early universe. Or here you can go with what you could reach if you use the AGMX experiments or other microwave cavity experiments looking for axion dark matter for search for gravitational waves. Or here you use the lumped elements, things like dark matter radio for gravitational wave experiments. So you see, so this would, at least now these experiments, they would already be better than the known limits which are already established, and it's very well. So I think there's a big motivation to go to higher sensitivities in this direction, and so axial dark matter searches and gravitational wave searches in this ultra high frequency range, they could cross fertilize each other. So thank you. With that, I would like to end this, and the floor is open again for questions, maybe not only for today, but for all the days and so on.
So please, any questions? Comments?
So you can always reach me via email and so on if you have some question and so on. And also my tutors there, I think they should be also available for such things. There's in the chat, there's something, but I don't know.
In the chat, they are thanking you, a lot for these wonderful lessons. So this is really what we all think.
Okay.
And thank you also for giving the student the possibility to send you email and ask questions when they will study more in detail your
I will send you the lecture from today. I'm preparing it and send you immediately.
One moment. There is one person that is again, he is thanking, all the people are thanking you. So,
Alles klar. Good. Thank you very much.